The view of the starry night sky is simply overwhelming. But the longer we marvel at the thousands and thousands of twinkling objects in the firmament, the bigger a fundamental question appears. Where did it all come from? When did the very first stars in the cosmos shine? What do they look like? And how long have they existed at all? Excitingly, experts may have finally found the answers to all these stellar questions. A research team has actually managed to uncover the spectral signature of the earliest generation of stars in a galaxy 13.4 billion light-years away. The exciting thing is that these so-called population 3 stars also contain primordial gas clumps and thus a component that takes us straight back to the beginnings of the universe. The list of ingredients for the star recipe is surprisingly straightforward. All it takes is gas and dust and the friendly assistance of gravity. In detail, stars are born when clouds of gas and dust contract under their own gravity. And once enough mass is accumulated, the pressure and temperature rise so much that fusion reactions are set in motion. Once the nuclear fire has been ignited in the core, the cosmos is enriched by a wondrous, brightly shining celestial body. So much for the basics. But how was the original starlight actually switched on? Or, to put it more precisely, how did the very first stars in the cosmos come into being? In this regard, the experts point to the trio of hydrogen, helium, and a little lithium, which, according to current doctrine, was created shortly after the Big Bang around 13.8 billion years ago. A few 100 million years later, the first stars formed from this. More precisely, this happened in so-called mini-halos, or in other words, in clumps of compressed hydrogen and helium gas, which were collected by local accumulations of dark matter. However, since no heavier elements were available to the stellar outgrowths at that time, they also differed considerably from their present-day counterparts. They had hundreds of times more mass than later stars, which meant that they were consequently hotter, used up their fuel more quickly, and thus only existed for a few million years. As is well known, a star always dies in an explosive supernova. But here too, the first stars in the cosmos can confidently be described as different. As soon as a celestial body with 140 to 260 times the mass of the Sun bid farewell to the cosmic stage, the explosion initially resulted in a so-called pair instability, which means nothing more than that the radiation generated in the star became so energy-rich that pairs of electrons and positrons were created. Ultimately, the star's core collapsed into a black hole, and its outer layers were catapulted into space in an explosion many times more energetic than an ordinary supernova. Are these the very first stars in the cosmos? While experts have actually already managed to locate relics and possible radiation effects of these early population 3 stars, direct evidence of the first generation of stars has been lacking. But how do you actually discover the stellar pioneers of the universe? For a long time, the sobering answer to this question was not at all, mainly because the resolution of our telescopes has so far simply not been sufficient to identify stars at such enormous distances. Fortunately, however, scientists also have a loophole of a somewhat different kind at their disposal because newer models suggest that population 3 stars could also have formed in residual clumps of untouched prime Val gas in later galaxies. On paper, these clumps should, in turn, be found in the galaxy halo, the spherical region in which the galactic disk is embedded. To put this theoretical prediction to the practical test, a team led by Roberto Maiolino from the University of Cambridge has reached out to the galaxy GNZ11, and for good reason. After all, the collection of stars 13.4 billion light-years away already existed around 430 million years after the Big Bang. In order to search for the typical spectral signatures of population 3 stars, which are characterized by broadened spectral lines of ionized helium and the absence of heavy elements, the researchers again turned to Webb's NIR spec. Lo and behold, the observation with a high-resolution infrared spectrograph should indeed reveal a spot in the halo, in the outer region of GNZ11, which attracted attention with intense helium-2 spectral lines. Conversely, there must once have been an extended area of excited helium gas here, and the fact that no other elements could be detected there, according to the experts, literally screamed that the gas clump must present itself in a fairly original form. This is supported by the fact that the origin of the helium signature lies far from the black hole in the galactic center, which rules out the possibility that it was excited by the radiation of the mass monster. So, there must be something else in the gas clumps that is responsible for this, and most likely, these are intensely radiating clusters of young giant stars of the very first generation. According to the theory, the remnants of the primordial gas can collapse to form population 3-star clusters. This assumption was confirmed by the follow-up analysis of the spectral data, so the experts may have actually captured the direct signature of the stellar primitive babies of the cosmos for the first time in the halo of GNZ11. But that's not all, because, while the giant stars are enthroned in the midst of a prime valve gas cloud, the researchers have determined that each of them weighs up to 500 solar masses. However, since research into the starlight hour 0 has only just begun, astronomers now hope to find out more about these early stars and their development through further observations of GNZ11. Why the first stars remain a mystery, and indeed, it's the development of the first stars in particular that still poses a great mystery to experts. As already mentioned, the first stars only formed hydrogen, helium, and a little lithium. The heavier elements were only created later by nuclear fusion in stars and supernovae. This circumstance seems all the more confusing when we consider that these same heavier elements play a fundamental role in the processes of today's stars like the Sun. This applies in particular to carbon, nitrogen, and oxygen, which act as a kind of mediator in the so-called CNO cycle. To put this into context, the CNO cycle is one of the possible fusion reactions by which hydrogen fuses to form helium. But even in the oldest stars still in existence today, which are thought to be the direct descendants of the first generation, researchers identify only very few heavy elements. This may be due to the weak supernovae of Yo. The corresponding model is based on the assumption that the first stellar explosions were by no means many times more energetic, but significantly weaker than those of today. Consequently, they hardly produced any heavy elements. Well, with the exception of calcium. Unfortunately, it's not possible to say with absolute certainty where this came from. One consideration is based on the assumption that even the smallest amounts of carbon, nitrogen, and oxygen could have been enough to trigger CNO reactions in the first stars. In the context of such a process, calcium would have been produced as a kind of byproduct. But confusingly, new findings show that the fusion reaction of hydrogen to form helium not only produces calcium but also partially breaks it down again. In view of this, it seems unlikely, to put it mildly, that the existence of the detected calcium can be explained by a CNO cycle in the first stars. The picture of faint supernovae is thus seriously undermined, but what could shed more light on this than the study of a contemporary supernova remnant? Were the first stars not as massive after all? Researchers at the Chinese Academy of Sciences did, in fact, notice an old star with an unusual chemical composition in the data from the Lamos telescope. A few more observations with the Subaru telescope in Hawaii later, there was no longer any doubt that the celestial body had significant differences in the frequency of neighboring elements in the periodic table. In detail, elements with odd atomic numbers, such as sodium and cobalt, occur significantly less frequently than elements with even atomic numbers, such as magnesium and nickel. According to the researchers, this fact proves nothing more than that the object actually emerged from the remains of an extremely massive star of the first generation. Future studies should uncover even more such old stars with comparably strange compositions and give us an impression of how many stars of which masses existed in the early days of the universe. Surprisingly, it appears that the very first stars were not as massive as previously thought. While previous model simulations still indicated that the population 3 stars were true giants of 100 to 1,000 solar masses, this fact simply does not match our real observations. More specifically, This applies to the observations of the indirect evidence of the first stars, which experts can deduce from the elemental ratios of the subsequent populations. However, the aforementioned ratios of very old, metal-poor stars suggest that the first stars only weighed between 12 and 60 solar masses. But how can these deviations be explained? Possibly with gravitational turbulence in the center of the many halos at that time. These turbulent flows could have disrupted the dense centers of the gas clouds and thus prevented or delayed the complete collapse of the cloud. As a result, not a single massive stellar giant was formed, but dense clumps of gas that collapsed into several smaller stars. However, these were not up to 1,000 solar masses in weight, but only between 8 and 59 solar masses. This mass range is consistent with our studies of extremely metal-poor stars and provides a plausible explanation for why the indirect observational data differ so much from previous models. And now, we'll give you a plausible explanation for your click on the subscribe button. Press the thumbs up and subscribe now so you'll never miss a new video from us again. We'll see you soon.